These are sample problems related to our topic, Reheat Rankine Cycle. So for this problem, we are given with a Reheat Rankine Cycle with a power output of 100 megawatt. You can see here. And the steam enters the high turbine at 10 megawatt and 500 degrees Celsius. The entrance of the high pressure turbine is our point 3. So the pressure and temperature at point 3 is 10 megawatt and 500 degrees Celsius. The low pressure turbine is at 1 megapascal and 500 degrees Celsius, and that is 0.5. So the low pressure turbine is the entrance is at 0.5. So the pressure and temperature here is 1 megapascal and 500 degrees Celsius. Steam leaves the condenser as saturated liquid. So the exit of the condenser is at 0.1, and that is at a saturated liquid at 10 kilopascal. So the pressure at this point is 10 kilopascal. We're given with isentropic efficiency of the turbine is 80% and the pump is 90%. This is the reason why we have here the deviation. Instead of having an isentropic process, we have an actual reheat Rankine. We have an actual reheat Rankine. So we have 0.6A. Same also with the high pressure turbine. So both turbine are actual with an isentropic efficiency of 80%, and the pump also has isentropic efficiency of 90%. It's actually an actual cycle. So this is the answer for our this question here, to show the cycle in a TS diagram with respect to the saturation lines. So this is the TS diagram of this cycle. So what we're going to compute now is the quality, or if it is superheated, then we're going to compute the temperature of the turbine at the turbine exit. The turbine exit is our 0.6A. The thermal efficiency of the cycle and the mass flow rate of the steam. So first is to tabulate the properties. So as you can see here, we have 6 points. We have 0.1, 0.2A, 0.3, 0.4, A, 0.5, and 0.6A. So that's why we have here 6 points. At 0.1, it is given as a saturated liquid at 10 kPa. That's why we have 10 kPa. That's why the quality is 0%. At 0.2, this is in the subcooled liquid. That's why it's subcooled liquid. And the pressure here, this green line here represents the same pressure. That's why the pressure at 0.3 is the same pressure at 0.2 and 0.2A. The pressure at 0.3 is 10,000 kilopascal, or that's 10 megapascal. That's why we have here 10,000 kilopascal. Same also with 0.3, but this time 0.3 is in the superheated vapor region. That's why it's superheated vapor at 10,000 megapascal. And the temperature is given as 500 degrees Celsius. That's in Kelvin as 773.15 Kelvin. At 0.4, this is still a superheated vapor, and with the same pressure as this is a constant pressure line. That's why the pressure at 0.5 is the same pressure as 0.4A. So the pressure at 0.5 is the same pressure at 0.4A. That's why it's 1,000 megapascal, 1,000 kilopascal, or 1 megapascal is given. At 0.5, it is given as at the enters the low pressure turbine as 1 megapascal and 500 degrees Celsius at 0.5. So that's why we have your superheated vapor with pressure and temperature as follows. And then we have at 0.6, assuming that it's an ideal process, then 0.6 should be a mixture with the same pressure as 0.1. This is a constant pressure line. That's why it's 10 kilopascal. So the green ones, these are the given from the problem and the value that we can get by analysis. And the rest, we're going to use table to calculate those values. At 0.1, since this is a saturated liquid, and for saturated liquid, if you only have one property given, then we can use the software to compute the other properties. So that's why entering 10 kilopascal in our software at saturation points, then we have these values. And then we can see that process 1 to 2. Take note that in this table, we are going to get the ideal points first, not the actual. That's why point 1 to process 1 to 2 is isentropic process. So they have the same entropy. So that's why it's 0.6492. And since this is a subcooled liquid, we need properties. So since we already have 10 kilopascal and 0.6492, we just plug it in at the specified state points in the software, then we can get the rest of the properties. Now at point P, this is a superheated vapor. And since we have two properties here given, then we can get the other properties using our software. And then at point 4, this is a superheated vapor. But process 3 to 4 is an isentropic process. So you can see this is a vertical line. That's why it's the same as point 3. So they have the same entropy. And since we have two properties now, then we can plug it in at specified state points and we can get the other properties. At point 5, we are given with two properties, so we can get the rest of the properties. And at point 6, since process 5 to 6 is isentropic process, then they have the same entropy. And same also with the other points. We can use these 2 points to get the remaining properties. We're able to complete now our table using the software. So we have these properties. These are the ideal value of enthalpy at the different points. So you can see point 3 has the point 5 has the highest enthalpy. And that is the entrance to the low pressure turbine. So first, we need to calculate the actual points. So if you can look at our diagram, we have an actual cycle with points H6A, point H64A, and point H62A. So these are the actual values because of the isentropic efficiencies. To calculate that, we will use our formula that the isentropic efficiency of the turbine is H5 minus H6A over H5 minus H6A. This is for the low pressure turbine. So these are the enthalpies at the low pressure turbine. We have H5. The values that don't have letter A, these are the value from the table, and A is what we are going to compute. And since we are given with the isentropic efficiency of the turbine, and that is 0.8, then we can plug it in here in the formula, as well as the value of H5 and H6 in the table, that is 3479.1 and 2461.1, so that our only unknown is H6A. So our H6A is 2664.7. As you can see, if we compare it with H6, our actual enthalpy at 0.6 is actually higher than the ideal. Next is to calculate H4A. And since this is still a turbine, then we can use the isentropic efficiency of the turbine. So the points at the high pressure turbines are 0.3 and 0.4. So we are going to plug in the same isentropic efficiency of the turbine, 0.8, and then the table value of H3, that's 3275.1 and 2783.7. And then our unknown is H4A, so we calculate for that one. Our H4A is 2901.98 kilojoules per kilogram. And finally, for the pump, our isentropic efficiency is given as H1 minus H2 over H1 minus H2A. So it's the reverse, no? So for A, we're going to solve for that one by plugging in the value of H1 and H2 in the table, and the isentropic efficiency of the pump, which is 0.9. Our H2A is 203 kilojoules per kilogram. So we are able to compute now the actual value of enthalpies at 0.2, 0.4, and 0.6. So these are the actual, because we have an actual cycle. So we're going to calculate for the quality or temperature if the point is superheated of the steam at the turbine exit. So if you're going to look back at the TS diagram, the turbine exit is at point 6A. So we're going to look for the quality at point 6A. So that's why we have H6 here. So to calculate for the turbine exit, quality at the turbine exit, we can use this formula. So that is the actual enthalpy at point 6 minus the enthalpy of saturated liquid at that pressure, and then the difference of Hg and Hf at point 6. So using the steam table or the software, our HF6 is equals to HF at 10 kPa. So this is at the condenser. Same also with HG6, we're going to use Hg at 10 kPa. And thus, by substitution of these values here, as well as the H6A that we computed previously, we can get the value of X6 as 1.03. And since our X6 is greater than 1, so that meaning it is a superheated vapor. Because if it is equals to 1, then it's a saturated vapor. And greater than 1, it's a superheated vapor. So meaning, we need to compute the temperature, because if it is superheated, we're going to compute the temperature at the exit of the turbine. So to determine the temperature at the exit of the turbine, we're going to use the, since it's a superheated vapor, H6 is equal to the temperatures at H6A. So we're going to look for the temperature at H6A, which is 2664.7, and using also the pressure at 0.6, which is 10 kPa. Because take note that even if it is a superheated vapor, it still belongs to the same pressure line. That's why we can still use 10 kPa. So using pressure and enthalpy at 0.6A, then our temperature using the software is 361.21 Kelvin, or that is 88.06 degrees Celsius. So we're able to compute the quality as well as the temperature of the steam at the turbine exit. At the exit of the turbine, the temperature is 88 degrees Celsius. Next is the thermal efficiency of the cycle. So the thermal efficiency of the cycle, that can be computed if we have the turbine work and the pump work. So we need to compute first those values. So for the turbine work, we have two turbines, the high pressure turbine, that's WT1, and the low pressure turbine, that's WT2. So for the turbine, our equivalent turbine work is H3 minus H4A minus plus H5 minus H6A. So these are the different points at the turbine inlet and exit. So since we already have H4A, H3, and H5, we just substitute all the value. Our work of the turbine is 1,287.52 kilojoules per kilogram. For the pump work, that's just equals to H2A minus H1, or the change of enthalpy across the pump. So we're given with H2A from our previous calculation, and from the table, H1 is 191.81. The pump work is 11.19 kilojoules per kilogram. So for the net work, that is just a difference between the turbine work and the total pump work. So that is 1,276.33 kilojoules per kilogram. And then, efficiency is also a function of the total heat input in the boiler. And that is, the total heat input in the boiler is equals to the heat in the boiler plus the heat because of the reheating. So our total Q in is H3 minus H2A plus H5 minus H4A. So H3 minus H2A is for the boiler, and H5 minus H4A is the reheating. So substituting the values, our total heat input is 3,749.22 kilojoules per kilogram. So we can compute now the thermal efficiency using the formula work net over heat input. So the thermal efficiency is equals to 34.04%. So the thermal efficiency of this reheat Rankine cycle is 34.04%. And finally, for the mass flow rate, we can calculate the mass flow rate using the formula power is equals to mass times the work net. So substitute from the given, since power is given as 100 megawatt and that's equals to 100,000 kilowatt, then our power is just 100,000 equals to mass times the work net. Our mass flow rate is 778.35 kilogram per second. So those are the different quantities needed for this problem if we have an actual cycle with isentropic efficiencies of the turbine and the pump. What if we're given with the same value, but this time there are no isentropic efficiency? So meaning if they are not given, we have an ideal reheat Rankine cycle. So for this problem, this is an ideal reheat Rankine cycle. If that is the case, we are just going to use the value from the table which we already calculated previously because this is the same given as before. But this time, we have an ideal cycle. So those that do not have deviation. So wala na tayo deviation wala na tayo deviation. Okay, wala tayo mga isentropic efficiencies, or the isentropic efficiency is equals to 100%. If that is the case, we can still compute for the quality by using the same formula that we used previously. So this time, instead of using H6A, since this is an ideal cycle, we're going to use now the actual values at 0.6, and that is H6. So that's 2461.1. That's why we have here 2461.1. Our H6, if we have an ideal cycle, is 94.86%. And since X6 is less than 1, then this is a mixture. And if that is a mixture, then no need to calculate the temperature, because basically the temperature is just equals to the temperature at 0.6, which is 318.96 Kelvin. So this time we have a mixture instead of a superheated vapor. For the thermal efficiency, we can still use those formula, but this time instead of using H4A and H6A, we use the value in the table, which is H4 and H6. So we substitute those values here. We can get the turbine work as 1,609.4. And for the pump work, we're going to use now H2 instead of using H2A. H2 is 201.88. So that's why we have this one. Our pump work is 10.07 kilojoules per kilogram. So the net work is just the difference of that value, and that is 1599.33. For the heat input, it's just the same formula, but this time we're not going to use H2A and H4A, but the value in the table. So our total heat input is 3,868.62. So our thermal efficiency is equals to 41.34%. Actually, this is greater than the actual cycle, because in the actual cycle we have 34%, but this time it's 41. So the ideal cycle is actually greater. The mass flow rate, we can still use the same formula, and then work net from this problem is 1599.33. That's why our mass flow rate is actually smaller. That's 62.52 kilogram per second. So based on the results, we can infer that the thermal efficiency for the actual cycle is actually lesser than the ideal, and it also requires greater mass flow rate than the ideal cycle. So that is how to analyze the ideal and actual Rankine reheat cycle.